Below, we have this problem. We have a commutative diagram of linear maps with two horizontal exact sequences. I have to show that if phi 4 is injective and phi 1 is surjective, then this statement is true. Okay, let's begin by observing what we're essentially given by the fact that phi 4 is injective and phi 1 is surjective. For surjectiveness is directly related to the image, so it makes sense to review this quad. So the composition beta 1 phi 1 is obviously going to be equal to phi 2 alpha 1. Now if we're to take the image of this composition is going to be just the image of beta 1 because phi 1 is surjective. So the image of beta 1 equals to the image of phi 2 alpha 1, and as a result, since this is an exact sequence, we can also write this down as kernel of beta 2 equals to the image of phi 2 alpha 1. Cool. Now let's observe what the fact that phi 4 is injective gives us. Well, since it's injective, then the kernel of phi 4 is going to be just 0. So let's review two compositions. Phi 4 alpha 3 is going to be equal to beta 3 phi 3. Now we were to take the kernel of these equal compositions. Then since kernel of phi 4 is 0, the kernel of this composition is going to be the kernel of alpha 3. So the kernel of alpha 3 is equal to the kernel of beta 3 phi 3. Okay, and now if we were to review this, we can safely say that the kernel of phi 3 is a subset of kernel of beta 3 phi 3. That is because if there's an element of E3 such that phi 3 of that element is equal to 0, then well, in this composition we're gonna get B3 of 0, and since we're working with linear mappings, then that's gonna be 0 too. So kernel of phi 3 is gonna be a subset of kernel of beta 3 phi 3, and since it's equal to kernel alpha 3, we can write this down. And we can also say that the kernel of alpha 3 is also the image of alpha 2. Okay, so we have quite a few interesting things going on. We know that kernel of phi 3 is a subset of image of alpha 2. Another thing that we can do is we can review this quad that contains both the alpha 2 and the phi 3. So let's take phi 3 alpha 2 equals beta 2 phi 2. Now we were to look into the kernel of these compositions. Kernel phi 3 alpha 2 equals well, the kernel of beta 2 phi 2. Now, thing is, earlier we have worked with this thing, and well, we can rewrite it as phi 2 of image of alpha 1 And this essentially implies that the kernel of this composition is going to be the image of alpha 1. Now again, we're applying the fact that we're working with the exact sequences, so that's going to be the kernel of alpha 2. Now we have an interesting thing. We know that kernel of phi 3 alpha 2 is going to be equal to the kernel of alpha 2. And while this has some implications, that means that there is no such element x such that alpha 2 of x is not equal to 0, and phi 3 of alpha 2 x is equal to 0. And this has an interesting implication. That means that the image of alpha 2 intersected with the kernel of phi 3 is the set containing 0. Now let's look into what 0 we're working with. That 0 is of E3, so let's note that. Now, if we were to go back a little, we have made this conclusion earlier. The fact that kernel of phi 3 is a subset of image of alpha 2. And now this together, since kernel of phi 3 is a subset of image of alpha 2, then kernel of phi 3 is also the intersection of kernel phi 3 with the image alpha 2. So kernel phi 3 is equal to the 0 set, like this. Oh, well, this can also be represented as alpha 2 kernel alpha 2. Now, notice if we were to go back, it's almost here. The only thing we have left to do is we can show that kernel of phi 2 is a subset of kernel of alpha 2. So suppose we have an element x belonging to kernel of phi 2. Now let's go back to the diagram again, and let's look probably into this part here. Let's look into compositions beta 2 f2, not f2, phi 2, and phi 3 alpha 2. So beta 2 phi 2 is equal to phi 3 alpha 2. Okay, now knowing that, you can get a specific value of these compositions. Well, since x is part of the kernel of phi 2, then in this composition, it's gonna be just beta 2 of phi 2 of x. Next we have beta 2 of 0. We're working with a linear mapping, so that's just 0. Now let's look into what 0 we're working with. Beta 2. So supposedly 0 of F3. Let's look into that again. Okay, yes, phi 3 goes here. Looks correct. So phi 3 alpha 2 of x Now, this implies that x belongs to the kernel of phi 3 alpha 2. Now, what we have to do is have to show that actually we don't even have to show anything. From this, phi 3 is injective, so this is just going to be equal to the kernel of alpha 2. So for every x belonging to the kernel of phi 2, x is gonna belong to kernel of alpha 2. Therefore, alpha 2 of kernel of phi 2 is gonna be equal to alpha 2 of kernel of alpha 2. So now we can go back, grab this statement, and finally conclude that kernel phi 3 is equal to alpha 2 of kernel of phi 2. And let's comb this in together. Now, I'm absolutely not confident in my answer, so if you're better at linear and abstract algebra than me, please, if you have seen an error in the video, point it out, because I'm really unsure of this answer. I'm like barely convinced it's true. Well, the way I proved it, that it's consistent and proper. That's it for today. Bye.